Over the past 60 years, cosmology has become ever more precise in its ability to account for the best available data about the universe. Many discoveries throughout our history have enabled us to better understand the universe around us. Even though we don't know everything, there are enormous sources of knowledge that have empowered us to draw far-reaching conclusions about our universe. We know what it's made up of in terms of matter, energy, radiation, and so on. We know that there are 400 billion within our galaxy and about 2 trillion galaxies are present throughout the visible universe. We know how the universe clumps and clusters together into galaxy groups, clusters and filaments, and how they're separated by vast cosmic voids. We know the scale of the cosmic distances defining these structures and how the universe is evolving over time. It's a remarkable story that all fits together beautifully in the framework of the Big Bang and general relativity theory. But along the way, experts have had to postulate the universe was not built for the human mind to understand. Up to now, all the stars, planets, and galaxies that can be seen today make up just 5% of the universe. The other 95% is made of stuff astronomers can't see, can't detect, or even comprehend. Worse, when we extrapolate back to the earliest stages of the universe and compare what we expect to observe, there are some big problems. Not long after the James Webb Space Telescope, or JWST, began beaming back from outer space its stunning images of planets and nebula last year, astronomers, though dazzled, had to admit that something was amiss. 8 months later, based in part on what the telescope has revealed, it's beginning to look as if we may need to rethink key features of the origin and development of the universe. Join us today as we dig deep into how the James Webb Space Telescope has debunked all modern theories of the universe. The James Webb Space Telescope is a breathtakingly glorious feat of engineering. Built on the Hubble Space Telescope's discoveries, James Webb is a giant leap forward in our quest to understand the universe and our origins. It is a premier observatory with a large infrared telescope that has an approximately 6.5 meter primary mirror. The most cutting-edge engineering allowed Webb to examine every phase of cosmic history, from the first luminous glows after the Big Bang to the formation of galaxies, stars, and planets, to the evolution of our own solar system. Launched at the end of 2021 as a joint project of NASA, the European Space Agency, and the Canadian Space Agency, the Webb, a tool with unmatched powers of observation, is on an exciting mission to look back in time at the first stars and galaxies, delivering and giving us a broader understanding of the origins of our universe. But the fact that the more curious we get about the great cosmic unknowns, the more unanswered questions our investigations of the universe will reveal. And the same is also true for James Webb. Indeed, one of Webb's first major findings was exciting in an uncomfortable sense. It discovered the existence of fully formed galaxies far earlier than should have been possible, according to the so-called Standard Model of cosmology. According to the Standard Model, which is the basis for essentially all research in the field, there is a fixed and precise sequence of events that followed the Big Bang. First, the force of gravity pulled together denser regions in the cooling cosmic gas, which grew to become stars and black holes. Then, the force of gravity pulled together the stars into galaxies. The Webb data, though, revealed that some very large galaxies formed really fast in too short a time, at least according to the Standard Model. This was no minor discrepancy. The finding is akin to parents and their children appearing in a story when the grandparents are still children themselves. Unfortunately, it was not an isolated incident. There have been other recent occasions in which the evidence behind science's basic understanding of the universe has been found to be alarmingly inconsistent. Take the matter of how fast the universe is expanding. This is a fundamental fact in cosmological science, the so-called Hubble constant, yet scientists have not been able to settle on a number. There are two main ways to calculate it. One involves measurements of the early universe, such as the sort that the Webb is providing. The other involves measurements of nearby stars in the modern universe. Despite decades of effort, these two methods continue to yield different answers. At first, scientists expected this discrepancy to resolve as the data got better, but the problem has stubbornly persisted even as the data have gotten far more precise. And now, new data from the Webb have exacerbated the problem. This trend suggests a flaw in the model, not in the data. Two serious issues with the standard model of cosmology would be concerning enough, but the model has already been patched up numerous times over the past half-century to better conform with the best available data. Alterations that may well be necessary and correct, but which, in light of the problems we are now confronting, could strike a skeptic as a bit too convenient. Physicists and astronomers are starting to get the sense that something may be really wrong. It's not just that some of us believe we might have to rethink the standard model of cosmology. We might also have to change the way we think about some of the most basic features of our universe. A conceptual revolution, if you will, that would have implications far beyond the world of science. A potent mix of hard-won data and rare-field abstract mathematical physics, the standard model of cosmology is rightfully understood as a triumph of human ingenuity. It has its origins in the Edwin Hubble's discovery in the 1920s that the universe was expanding, the first piece of evidence for the Big Bang. Then in 1964, radio astronomers discovered the so-called cosmic microwave background, the fossil radiation reaching us from shortly after the universe began expanding. That finding told us that the early universe was a hot, dense soup of subatomic particles that has been continually cooling and becoming less dense ever since. Over the past 60 years, cosmology has become ever more precise in its ability to account for the best available data about the universe. But along the way, to gain such a high degree of precision, astrophysicists have had to postulate the existence of components of the universe for which we have no direct evidence. The standard model today holds that normal matter, the stuff that makes up people and planets and everything else we can see, constitutes only about 4% of the universe. The rest is invisible stuff called dark matter and dark energy, roughly 28% and 68% respectively. Cosmic inflation is an example of yet another exotic adjustment made to the standard model. Devised in 1981 to resolve paradoxes arising from an older version of the Big Bang, the theory holds that the early universe expanded exponentially fast for a fraction of a second after the Big Bang. This theory solves certain problems but creates others. Notably, according to most versions of the theory, rather than there being one universe, ours is just one universe in a multi-universe, an infinite number of universes, the others of which may be forever unobservable to us, not just in practice, but also in principle. There's nothing inherently fishy about these features of the standard model. Scientists often discover good indirect evidence for things that we cannot see, such as hyperdense singularities inside a black hole. But in the wake of Webb's confounding data about galaxy formation and the worsening problem with the Hubble constant, you can't be blamed for starting to wonder if the model is out of joint. A familiar narrative about how science works is often trotted out at this point to assuage anxieties. It goes like this. Researchers think that they have a successful theory, but new data show it is flawed. Courageously rolling up their sleeves, the scientists go back to the blackboards and come up with new ideas that allow them to improve their theory by better matching the evidence. It's a story of both humility and triumph, and scientists love to tell it. And it may be what happens in this case too. Perhaps the solution to the problems the Webb is forcing us to confront will require only that cosmologists come up with a new dark something or other that will allow our picture of the universe to continue to match the best cosmological data. However, there is another possibility. We may be at the point where we need a radical departure from the standard model, one that may even require us to change how we think of the elemental components of the universe, possibly even the nature of space and time itself. Cosmology is not like other sciences. It's not like studying mice in a maze or watching chemicals boil in a beaker in a lab. The universe is everything there is. There's only one, and we can't look at it from the outside. You can't put it in a box on a table and run controlled experiments on it. Because it is all-encompassing, cosmology forces scientists to tackle questions about the very environment in which science operates. The nature of time, the nature of space, the nature of law-like regularity, the role of the observers doing the observations. These rarefied issues don't come up in the most regular science, though one encounters similarly shadowy issues in the science of consciousness and in quantum physics. But working so close to the boundary between science and philosophy, cosmologists are continually haunted by the ghosts of basic assumptions hiding unseen in the tools we use, such as the assumption that scientific laws don't change over time. But that's precisely the sort of assumption we might have to start questioning in order to figure out what's wrong with the standard model. One possibility, raised by the physicist Lee Smolin and the philosopher Roberto Manganbeira Unger, is that the laws of physics can evolve and change over time. Different laws might even compete for effectiveness. An even more radical possibility, discussed by the physicist John Wheeler, is that every act of observation influences the future and even the past history of the universe. Dr. Wheeler, working to understand the paradoxes of quantum mechanics, conceived of the participatory universe, in which every act of observation was in some sense a new act of creation. It is not obvious, to say the least, how such revolutionary reconsiderations of our science might help us better understand the cosmological data that is flummoxing us. Part of the difficulty is that the data themselves are shaped by the theoretical assumptions of those who collect them. It would necessarily be a leap of faith to step back and rethink such fundamentals about our science. But a revolution may end up being the best path to progress. That has certainly been the case in the past, with scientific breakthroughs like Copernicus's heliocentrism, or Darwin's theory of evolution and Einstein's relativity. All three of those theories ended up having enormous cultural influence, threatening our sense of our special place in the cosmos, challenging our intuition that we were fundamentally different than other animals, upending our faith in common sense ideas about the flow of time. Any scientific revolution of the sort we're imagining would presumably have comparable reverberations in our understanding of ourselves. The philosopher Robert Crease has written that philosophy is what's required when doing more science may not answer a scientific question. It's not clear yet if that's what's needed to overcome the crisis in cosmology, but if more tweaks and adjustments don't do the trick, we may need not just a new story of the universe, but also a new way to tell stories about it. But noting that despite the universe itself may be finite or may be infinite, the part that's accessible to us is finite. Even with the expanding universe, even with all the galaxies and stars and planet and molecules and atoms and subatomic particles in it, there's only so much we can assess. And those limitations, the total number of particles and the total amount of energy available in the universe, means there's only a finite amount of information we can determine about our cosmos. The total amount of information accessible to us in the universe is finite, and hence, so is the amount of knowledge we can gain about it. There's a limit to the amount of energy we can access, the particles we can observe, and the measurements we can make. That doesn't mean we're done, or that we shouldn't strive to learn everything we absolutely can. Only we can push the frontiers of knowledge back as far as they can go. There's a whole lot left to learn, and a whole lot of science that is yet to be revealed. If we continue to look, maybe the present unknowns will likely fall in the near future. But what is knowable is finite, and this implies that there are necessarily some things we may never know. The universe may yet be infinite, but our knowledge of it will never be. Regardless, the James Webb Space Telescope's upcoming discoveries are still worth looking forward to. The JWST has completed successfully its first year of scientific operation in the vacuum of space from its location nearly 1.5 million kilometers away from Earth. In addition to taking the most detailed and breathtaking images ever of the iconic celestial objects, Webb completed its first deep field campaign, turned its infrared optics on Mars and Jupiter, obtained spectra directly from an exoplanet's atmosphere, blocked out the light of a star to reveal the debris disk orbiting it, detected its first exoplanet, and spotted some of the earliest galaxies in the universe, those that existed at the cosmic dawn. Now, as the James Webb Space Telescope enters its second year of capturing images of the depths of space, it has already revealed a treasure trove of beauty from around the universe, both near and far from home. A major focus of the Webb mission is the investigation of cosmic dawn, which began roughly 1 billion years after the Big Bang. Also known as the epoch of reionization, this period is so named because the first galaxies emerged during this time. This led to the reionization of the neutral hydrogen that permeated the intergalactic medium, or IgM, causing the universe to be transparent. This era is considered the final frontier of cosmological surveys because the extreme redshift and presence of neutral hydrogen make it impossible to study this period in visible light. The lack of transparency during this period led to it being nicknamed the Cosmic Dark Ages. The only way to detect light from this period is by observing the 21-centimeter transition line, a part of the ratio spectrum inaccessible to modern-day instruments, or the H-alpha emission line, which is visible in the mid-infrared spectrum. According to a recent study, an international team led by the Capitan Astronomical Institute, or CAI, resolved the H-alpha emission line using data from the Webb's MIRI instrument, thus providing the first confirmed detection of galaxies at cosmic dawn. During Cycle 2, astronomers intend to push the boundaries even farther. For starters, Pi Carl Glazebrook of the Swinburne University of Technology and an international team were allotted 615 hours to conduct a JWST-wide Area 3D parallel survey. This will consist of pure parallel observations using JWST's near-infrared imager and slitless spectrograph, or NIRISS, of an area covering 1,000 square arc-minutes. The resulting survey, they claim, will provide spectra and redshift measurements for 60,000 galaxies from cosmic noon to cosmic dawn, circa 10 to 11 billion to 13 billion years ago, from the first stars and galaxies to the birth of the second generation of stars, or population 2 stars. Such a large area redshift survey will allow us to measure 3D clustering in the cosmic growth era, revealing the detailed connection between dark matter halos and assembling baryons. It will also provide a benchmark set of stellar mass functions for complete spectroscopic type defined samples, address the origin of galactic quenching, provide 2D abundance and age measurements of galaxies measuring galactic buildup, and provide a census of rare Z greater than 11 bright galaxies and other rare objects at all redshifts. The size of the survey will also enable data-driven discovery with advanced machine learning approaches, revealing novelties and surprises in the early universe, Carl Glazebrook and his research team said. In addition, Pi Hakim Atek of the Institute of Astrophysics at Paris and his colleagues proposed the gravitational lensing and near-cam imaging to probe the early galaxy formation and sources of reionization, or GLIMPS they call it, observation campaign. By taking ultra-deep images with Webb's near-infrared camera, the NIRCam, Atek and his team will observe low-mass galaxies a few 100 million years after the Big Bang. During their 148 hours of observation, they hope to investigate the mechanisms governing galaxy formation, such as gas accretion, star formation, and the subsequent feedback inhibiting further star formation. This, they claim, will achieve three main goals. We propose, they say, to combine the power of strong gravitational lensing with ultra-deep near-cam imaging to achieve these three main goals. Number one, to measure the prevalence of faint galaxies at a z greater than 6 to establish, for the first time, key observational benchmarks for galaxy formation models, which have never been confronted to this uncharted territory. Secondly, strongly constrain the contribution of the faintest galaxies towards cosmic reionization. And thirdly, probe the typical galaxy population during the Dark Ages that remains out of reach of current programs. Professor Daniel Einstein of Harvard University and an international team were awarded 137.1 hours for their proposal, unveiling the redshift frontier with JWST. This will consist of a deep 6-filter medium-band imaging survey with a NIRCam to identify galaxies at the redshift frontier z equals greater than 15. The properties of these very early galaxies will test and inform theories of galaxy formation and allow astronomers to make discoveries about the physics of the early universe. This includes theories about the possible presence of early dark energy to explain the discrepancy between measurements of cosmic expansion, aka the Hubble tension. They also plan to conduct this survey parallel to a deep multi-object spectroscopy campaign conducted with NIRSpec of galaxy candidates in and around the Hubble Ultra Deep Field, or HUDF. These spectra will provide detailed information about individual high redshift galaxies, not just stacks or averages, allowing us to study the chemical enrichment, stellar populations, star formation histories, and nuclear black holes in the first billion years of the universe, they state. In addition, one of the most anticipated aspects of the Webb mission is how it will assist with the transition currently taking place in exoplanet science. Whereas astronomers were largely focused on the discovery process in the past, improved instruments, methods, and analytics are shifting the focus towards characterization. To date, the vast majority of exoplanets have been detected by indirect means, which meant that constraints on their habitability had to be inferred based on their parent star, the distance at which they orbited, and their respective masses. But thanks to Webb's superior infrared optics and sensitivity, astronomers look forward to being able to directly image exoplanets and obtain spectra from their atmospheres. In particular, they hope to direct Webb's mirrors toward nearby M-type or red dwarf stars and their rocky planets, many of which have been confirmed in recent years. In addition to being the most common stars in the universe, accounting for about 75 to 80%, red dwarfs are also likely to support rocky planets within their habitable zones, or HZs. However, these planets are likely to be tidally locked with their suns, and red dwarfs are prone to flare activity, which raises questions about their long-term ability to retain atmospheres. To address this mystery, Dr. Shubham Kanodia of the Carnegie Institution of Washington and his team were awarded 132.39 hours for their program titled Red Dwarfs and the Seven Giants. This sweetly named study will characterize the atmospheres of giant rocky planets around M-type stars to address one of the JWST's primary science goals: how atmospheric composition can affect a planet's formation and evolutionary history. This will consist of Kanodia and his team using Webb's near-infrared spectrometer, or NIRSPEC, to observe short-period Jupiter-sized planets around red dwarfs, which pose challenges to current theories about planet formation and represent an extreme regime that is poorly understood. By comparing the atmospheres of 7 M-dwarf short-period Jupiters to the gas giants that orbit our Sun, they hope to characterize their atmospheric composition and metallicity and compare them to gas giants that orbit more massive yellow-type or F-type Sun-like or G-type and orange dwarf K-type stars.
Most of us are familiar with the standard narrative of how the universe began. There was an infinitely dense point of an infinite temperature with no size called a singularity. This singularity exploded, creating all the space, energy, and matter that we consider to be our universe in an event called the Big Bang. Between 10 to the power of -36 seconds and 10 to the power of -32 seconds, space expanded exponentially, growing much, much larger in size. After this period, space continued to expand, but at a much slower rate, and eventually, we see the universe that we observe today. This is the inflationary Big Bang theory, the most popular and broadly accepted theory of how the universe began. But for a few physicists, the premier theory doesn't paint an accurate picture of the evolution of our universe. Rather, they say that the universe existed before that point, stretching forever into the past as well as the future. While the universe is expanding today, it was contracting in the time before the Big Bang. In this picture, the Big Bang isn't so much a bang, but a bounce, a moment when a shrinking universe reversed course and began to grow. And according to their theory, the universe could bounce again. Today's expansion could be followed by collapse in the far future, followed by another bounce. Some physicists have suggested this bouncing could be infinite. This, of course, is counter to the way most cosmologists see it, where everything started with the Big Bang. But what is noteworthy here is this is not the only theory that dares to challenge the pinnacle theory of cosmology. Renowned physicist Brian Cox also challenges the Big Bang theory, asserting that something cannot emerge from nothing. Adding a bit of tension, the James Webb telescope has made a bunch of unexpected discoveries that contradict the notion that the Big Bang marked the beginning of the universe. All of these raise a question. If the Big Bang wasn't the beginning of the cosmos, then what was it? Could the universe start with a bounce, or something else entirely? Join us as we dig deep into one of the thorniest in physics. The idea that the universe had a beginning, or a day without a yesterday, as it was originally known, goes all the way back to Georges Lemaitre in 1927. Although it's still a defensible position to state that the universe likely had a beginning, that stage of our cosmic history has very little to do with the hot Big Bang that describes our early universe. Although many laypersons and even a minority of professionals still cling to the idea that the Big Bang means the very beginning of it all, that definition is out of date. The Big Bang now is not the birth of time and space. We know that today, in 2023. In fact, there's a ton of evidence that points to a non-singular origin to our universe. We never achieved those arbitrarily high temperatures. There's a cutoff. Instead, our universe is best described by an inflationary period that occurred prior to the Big Bang. And the Big Bang is the aftermath of what occurred at the end of inflation. Let's walk through what that looked like. During inflation, the universe was completely empty. There were no particles, no matter, no photons, just empty space itself. That empty space had a huge amount of energy in it at every location, with the exact amount of energy slightly fluctuating over time, by about 1 part in 30,000 on average. As the universe inflates, expanding in a rapid, relentless fashion, those fluctuations get stretched to larger scales, while new, small-scale fluctuations are created atop them. This superposition of fluctuations, of small scales atop intermediate scales, atop large scales, atop superhorizon scales, is one of the defining predictive features of cosmic inflation. This continues as long as inflation goes on. But inflation will come to an end randomly, and not in all locations at once. In fact, if you lived in an inflating universe, you'd likely experience a nearby region where inflation came to an end, while the space between you and it expanded exponentially. For a brief instant, you might even be able to detect what happens at the start of a Big Bang, before that region disappeared entirely from view. In an initially relatively small region, perhaps no bigger than a human-sized hamster ball, but perhaps much larger, the energy inherent to space gets converted into matter and radiation. The conversion process is relatively fast, taking approximately 10 to the power of negative 33 seconds or so, a brief amount of time, but nonetheless one that is not instantaneous. As the energy bound up in space itself gets converted into particles, antiparticles, photons, and more, the temperature starts to rapidly rise, from just a few degrees above absolute zero to perhaps 20 Kelvin or so, over that same brief time interval. Because the amount of energy that gets converted is so large, everything will be moving close to the speed of light. All quanta will behave as radiation with so much kinetic energy inherent to them, regardless of whether the particles are massless or massive. It doesn't matter under these conditions. This conversion process is known as reheating and signifies when inflation comes to an end and the stage known as the hot Big Bang begins. In terms of the expansion speed, you'll witness a tremendous change from all prior behavior when the hot Big Bang first commences. In an inflationary universe, space expands exponentially, with more distant regions accelerating away relentlessly as time goes on. But when inflation ends, the universe reheats, and the hot Big Bang starts, more distant regions will now recede from you more and more slowly as time goes on. From an outside perspective, the part of the universe where inflation ends sees the expansion rate there drop, while the inflating regions surrounding it see no such drop. Under inflation, the distance to any object would double after a certain amount of time, and once that same amount of time elapses, that distance doubles yet again and again and again. The process is relentless. But once the Big Bang begins, all of that changes, as the expanding universe immediately slows down once the first moment of expansion elapses. Probability-wise, it's extremely likely that from the perspective of whatever region of inflating space you're in prior to the Big Bang, you'll experience inflation ending in nearby regions many times. These locations where inflation ends will quickly fill with matter, antimatter, and radiation, and expand more slowly than the still inflating regions do, leaving you, in the inflating region, as a typical region within space-time dominating its volume. These regions, where hot Big Bangs occur, will expand away from all the other locations where inflation still goes on exponentially, meaning they will very quickly recede from one another's view. In the standard inflationary picture, because of this expansion rate change, there's virtually no chance that any two universes, where separate hot Big Bangs occur, will ever collide or interact. Finally, the region where we will come to live gets cosmically lucky, and inflation comes to an end for us. The energy that was inherent to space itself gets converted to a hot, dense, and almost uniform sea of particles. The only imperfections and the only departures from uniformity correspond to the quantum fluctuations that existed and were stretched across the universe during inflation. The positive energy quantum fluctuations will correspond to initially overdense regions, while the negative energy fluctuations get converted into initially underdense regions. But that's still enough to serve as the eventual seeds of cosmic structure. We cannot observe these density fluctuations today as they were when the universe first underwent the hot Big Bang. There are no visual signatures we can access from that early on. The first one we've ever accessed comes from 380,000 years later, after they've undergone countless interactions, Even at that, we can extrapolate back what the initial density fluctuations were and find something extremely consistent with the story of cosmic inflation. The temperature fluctuations that are imprinted on the first picture of the universe, the cosmic microwave background, give us confirmation of how the Big Bang began. However, there are a lot of inconsistencies between the cosmic microwave background and our current model of cosmology. We're missing something. These can be summarized in 4 anomalies. First, on very large scales, the universe isn't acting like we think it should. Second, light from the cosmic microwave background will be lensed by matter in between us and the cosmic microwave background. This means that matter acts like a giant lens, bending and changing the amplitude of the light behind it. The amount that this happens is not consistent with our current model of the universe. This is such a significant problem it has sometimes been called a crisis for cosmology. Third, the 2 hemispheres of the cosmic microwave background sky have different average temperatures. This doesn't make a lot of sense, since we believe that the universe should have started out uniform, on average. And last, the value of the Hubble constant, which describes how fast the universe is expanding, is different whether we measure it from the cosmic microwave background or from more nearby Cepheid stars. Taken together, these anomalies mean we're missing something fundamental in our understanding of the universe. The answer may lie in loop quantum cosmology. Loop quantum cosmology arises from loop quantum gravity. In loop quantum gravity, gravity itself is made of particles called quanta. These quanta come together to form the fabric of space and time. In this model of the universe, there is a smallest size of space itself, the Planck scale, or 10 to the power of negative 35 meters. Nothing, not even space itself, can be smaller than this. This means that the Big Bang couldn't exist in a universe with loop quantum cosmology. The universe could never get down to an infinitely small, infinitely dense point. Close to the Big Bang, when the universe was very small, really weird things happen mathematically. Infinities start to arise and threaten to tear the fabric of space-time itself. It's at these locations where loop quantum gravity can come in to provide corrections to the physics we already know. As Dr. Abhay Ashtekar at Penn State University, who led a study showing that the universe started in a bounce rather than a bang, said, "At such places, one has to use quantum geometry underlying loop quantum gravity. The quantum-corrected equations predict that there is an effective repulsive force. This means in these regions, when the universe is very small, the repulsion would result in a bounce. If our universe originated in a bounce, that means there was another universe before us. That universe went through its life, perhaps expanding and eventually contracting once again. As all of the matter and space-time of this universe came together, it ended in a spectacular fireball. Then, in a giant bounce, our universe was born, like a phoenix rising from the ashes of the old universe. This isn't entirely a new idea. Physicists have tossed around the idea of the Big Bounce for several decades. Even farther back, cyclic time is present in Hindu cosmology. If loop quantum cosmology is the correct model of the universe, in its infancy, the universe would have had very high curvature. To visualize this, think of a globe has positive curvature, a sheet of paper has flat curvature, and a saddle has negative curvature. If the universe was strongly curved when it was young, evidence of this would show up in the cosmic microwave background. When you look at the cosmic microwave background, you realize that it is not uniform. It's close, but there are small differences in temperature from one point in the sky to another. If you plot these temperature differences as a function of scale, you get one of the most powerful tools of cosmology, the angular power spectrum. Evidence of the curvature of the early universe would show up in the angular power spectrum of the cosmic microwave background. Some of these effects would show up at extremely large scales, larger than the size of the universe. This is a problem, obviously. We won't be able to observe it. However, luckily for us, These large scales interact with smaller scales, providing us with indirect evidence of this early phase of the universe. One of the effects of these interactions is to create the hemispherical anisotropy, says Ashtekar. In our current understanding of the universe, the probability that the two hemispheres of the sky would be different is very small. But with loop quantum cosmology corrections, the probability is enhanced and the observed anisotropy is no longer anomalous. That means that loop quantum cosmology would provide an explanation for anomaly number 3, why the hemispheres in the sky have different average temperatures. In addition, using the model of the universe that loop quantum cosmology provides solves the first 2 anomalies that we have seen in the cosmic microwave background: strange behavior at large scales and lensing. According to Dr. V. Srinath of the National Institute of Technology, Karnataka, this possibility that cosmic microwave background anomalies are not just statistical flukes, but rather effects due to quantum gravity happening very early in the universe is very exciting. But how sure are we that the universe originated in a big bounce? Except that, with all major claims, extraordinary evidence is needed. The idea that the universe originated in the Big Bounce has been suggested several times. We'll have to see if this one sticks. Another problem: our observations are limited, and it may just be that we are observing a part of the universe that is unusual. That's a problem called cosmic variance. As Dr. Donghui Zhang, a co-author of the paper and professor at Penn State University, said, "It is hard to confirm with 100% confidence because of the cosmic variance. But what is intriguing is that including this new possibilities can resolve 2 issues at the same time: the large-scale power suppression and small-scale lensing amplitude. Ruling out signs of an loop quantum cosmology-driven cosmic bounce in Planck, data means the cosmic microwave background anomalies remain unexplained. But an even larger cosmic issue lingers. Did the universe have a beginning at all? As far as advocates of the Big Bang are concerned, it did. But that leaves us with the inscrutable singularity that started everything off. Alternatively, according to theories of so-called cyclic cosmologies, the universe is immortal and is going through endless bounces. Although a bouncing universe may experience 1 or more cycles, a truly cyclic universe has no beginning and no end. It consists of a series of bounces that go back for an infinite number of cycles and will continue for an infinite number more. And because such a universe doesn't have a beginning, there's no Big Bang and no singularity. But physicist William Kinney of the University at Buffalo points out that there is a critical flaw lurks in the idea of an eternally cycling universe. That flaw is entropy, which builds up as a universe bounces. Often thought of as the amount of disorder in a system, entropy is related to the system's amount of useful energy. The higher the entropy, the less energy available. If the universe increases in entropy and disorder with each bounce, the amount of usable energy available decreases each time. In that case, the cosmos would have had larger amounts of useful energy in earlier epochs. If you extrapolate back far enough, that implies a Big Bang, like beginning with an infinitely small amount of entropy, even for a universe that subsequently goes through cyclic bounces. If you're wondering how this scenario doesn't violate the law of conservation of energy, we're talking about available energy. Although the total amount of energy in the cosmos remains static, the amount that can do useful work decreases with increasing entropy. New cyclic models get around the problem by requiring that the universe expands by a lot with each cycle. The expansion allows the universe to smooth out, dissipating the entropy before collapsing again. Although this explanation solves the entropy problem, Kinney and his University at Buffalo co-author Nina Stein calculated in their recent paper that the solution itself ensures that the universe is not immortal. As Kinney says, "I feel like we've demonstrated something fundamental about the universe, which is that it probably had a beginning. That implies a Big Bang occurred at some point, even if that event happened many bouncing universes ago, which in turn suggests that it took a singularity to get everything going in the first place." Kinney's paper is the latest in the debate over cyclic universes. but proponents of a universe without beginning or end have yet to respond in the scientific literature. Two leading proponents of a cyclic universe, astrophysicists Paul Steinhardt of Princeton University and Anna Ijas of New York University, declined to comment for this article. If the history of the debate is any indication, though, we may soon hear of a workaround to counter Kinney's analysis. Some physicists say the Planck data only rule out a bounce under a loop quantum cosmology model that can explain away the cosmic microwave background anomalies through the bispectrum, not other loop quantum cosmology bounce models that address anomalies using different mechanisms. Cosmologist Nelson Pinto Neto of the Brazilian Center for Physics Research, who has studied bouncing and other cyclic models, agrees that loop quantum cosmology bounces that account for the cosmic microwave background. Anomalies are likely off the table now, but he's more sanguine on the question of a cyclic universe. According to Nelson, existence is a fact. We are all here and now. Non-existence is an abstraction of the human mind. This is the reason he thinks that a cyclic universe, which has always existed, is simpler than one that has been created. However, as a scientist, he must be open to both possibilities. While the origin of our universe is still a mystery, there was a contentious argument about how the universe would end. The details of this narrative depend on the kinds of stuff the universe contains. The cosmic recipe determines how the universe changes in time and what kind of future it will have. There are essentially two possibilities. In one, the universe will keep on expanding forever, because stars have finite lives. At some point far in the distant future, they will be extinct. Stellar corpses will dot the universe, from slowly smoldering white dwarfs to black holes of different sizes. But drama can be added here, depending on what kinds of matter the universe contains. If the current recipe remains viable, there are three main ingredients: dark matter, dark energy, and the stuff we are made of, the normal matter of protons and electrons. Assuming normal matter and dark matter are stable in the long term, dark energy controls the future of the universe. If dark energy, this ether-like substance of unknown composition, is a constant, that is, if its density does not change and it maintains a fixed volume irrespective of cosmic expansion, then the universe's expansion will keep on accelerating. In extreme scenarios, it may have so much negative pressure that it will rip everything apart, decomposing matter back into its basic ingredients. Instead of from dust to dust, the cosmic epitaph would be from particles to particles. But it is also possible that dark energy is not like that, and that its negative pressure will fade with time, no longer fueling the universe's rapid expansion. Acceleration will lose pace, and the universe will retain the faded stars and their corpses, all resting far from each other, the ultimate cosmic loneliness. The sad part is that in a cosmos without room for entropy to grow, matter cannot reorganize into anything interesting. This is the cold cosmic death scenario. If nothing changes, time itself loses its function and reaches an end. Another possibility is that the expansion will slow down. If there is enough matter out there, it may revert itself and push the universe from expansion into contraction. Eventually, matter that was dispersed for billions of years will compact back into a small volume, heat up, reach crushing densities and, well, it depends. It may go into a big crunch, the inverse of the Big Bang, or it may reach a point of maximum contraction and then bounce outward into a new phase of expansion. This is the bounce universe model, where the universe trades periods of expansion and contraction, never quite reaching the point of infinite density or initial singularity. Time keeps on ticking, although each cycle needs new clocks. Every end of time marks the beginning of a new time, a new cycle of existence. This is a bit more comforting a view than cold death, even if each cycle involves destruction by fire. What we learn from our current cosmological models is how fortunate we are to exist precisely when it is possible to exist. Of course, there is no luck involved here. We exist now because this is when it is possible for matter to agglomerate into thinking blobs like us. In other eras, there would be no stars capable of sustaining life long enough for it to conjecture about its fate. So if time will end, it is because creatures like us will also end. In a universe without sentient beings, aware of time's passage, without the awareness of past and future, the very concept of existence is meaningless. That should give us pause when we consider how small we are in the vastness of space. Small, yes, but as far as we know, we are the ones who hold the whole cosmic history in our minds. That's all the...
Every image is a new discovery, and each will give humanity a view of the universe that we've never seen before.
Today represents an exciting new chapter in the exploration of our universe. This telescope is one of humanity's great engineering achievements.
The deeper you look, the less you understand should be the motto of our cosmology, especially in the presence of James Webb. The dawn of a new era in astronomy has begun as the world gets its first look at the full capabilities of the James Webb Space Telescope. In a mission more than 2 decades in the making, NASA launched the most expensive science probe ever built, a $10 billion telescope that will attempt to capture starlight from the first galaxies to be born in the fiery crucible of the Big Bang. Despite experiencing multiple delays, the Webb telescope has finally delivered the goods. However, the latest images captured by the Webb telescope are sending shockwaves through the scientific community as they call our entire understanding of galaxy formation into question.
All of a sudden we realize that we may have to rewrite all the textbooks about the beginning of the universe.
Join us as we dig into Webb's newest images, hinting at another universe at the edge of the universe. The generally accepted understanding of the universe is this. About 14 billion years ago, the Big Bang happened. In its early seconds, the laws of physics, as we understand them, didn't apply. All that would eventually become matter burst forth in a matter of seconds. First particles, like electrons and photons, and eventually neutrons and protons, the building blocks of our atoms. Early seeds of stars, planets, and galaxies expanded out from that momentous point in time and space. It spread in such a way that the universe became highly smooth. Smoothness, on an enormous scale, just means that things within the universe are relatively evenly distributed. That is, if you were to put a cube around one section of the universe, it wouldn't be much more dense than another randomly placed cube. On a smaller scale, like between galaxies or within a solar system, matter is lumpy and filled with clusters. Physicists theorize that shortly after the Big Bang, something called inflation occurred. Essentially, what was once a tiny, packed-together universe expanded out rapidly in a fraction of a second, and it continues to expand today. Inflation is part of the current standard model of the universe, called the lambda cold dark matter, or LCDM model for short. In LCDM, the shape of the universe's trajectory looks, in some depictions, like a funnel, its wide top growing and spreading further out over time. That's one interpretation, but there are others that have arisen out of the same bits of information that scientists can actually observe and measure in real life. That is, observational astronomy. The real-life information is crucial if scientists are to use models to make actual predictions about the future of our cosmos. Theoretical astrophysics is all about educated guesses that are shaped by the few things we do know for certain. Something called the cosmic microwave background contributes to a big part of that observable information. The cosmic microwave background is made up of the traces of radiation left over from an early phase of the universe. Radio telescopes can pick it up and then translate the waves into a heat map image of sorts. This image actually shows us how the contents of the universe were distributed about 400,000 years after the Big Bang, the earliest observable snapshot of a universe devoid of stars, solar systems, and galaxies. Everything was closer together and almost uniform. except for tiny fluctuations that became the matter forming stars and galaxies. This image serves as evidence that the universe started packed together and has expanded to where it is today. We also know that the universe continues to expand and can even measure, to some degree, how fast it's doing so. The cosmic microwave background also serves to confirm that an earlier version of the universe was very hot and our era is much colder. One way to test this model is by looking at very distant galaxies, equivalent to looking back in time to the first few 100 million years after the tremendous clap that started it all. The cosmos was simpler then, its evolution easier to compare against predictions. Astronomers first tried to see the earliest structures of the universe using the Hubble telescope in 1995. Over 10 days, Hubble captured 342 exposures of an empty-looking patch of space in the Big Dipper. Astronomers were astonished by the abundance hiding in the inky dark. Hubble could see thousands of galaxies at different distances and stages of development, stretching back to much earlier times than anyone expected. Hubble would go on to find some exceedingly distant galaxies. In 2016, astronomers found its most distant one, called GN-Z11, a faint smudge that they dated to 400 million years after the Big Bang. That was surprisingly early for a galaxy, but it did not cast doubt on the LCDM model, in part because the galaxy is tiny, with just 1% of the Milky Way's mass, and in part because it stood alone. But when the James Webb Space Telescope came along, our story of the universe has been thrown into disarray. NASA's $10 billion gamble, in full operation since summer 2022, has shown that galaxies formed much sooner after the Big Bang than scientists previously thought, and that some of them are unexpectedly large, absolutely brimming with stars. These findings have thrown the whole scientific community into a new reality in which their existing theories no longer apply. The earliest and most massive galaxies observed by James Webb so far stand to contradict the prevailing thinking in cosmology. That's because other researchers estimate that each galaxy is seen from between 300 and 500 million years after the Big Bang, but measures more than 10 billion times as massive as our Sun. One of the galaxies even appears to be more massive than the Milky Way, despite that our own galaxy had billions of more years to form and grow. That means if the masses are right, then we are in uncharted territory. We'll require something very new about galaxy formation, or a modification to cosmology. One of the most extreme possibilities is that the universe was expanding faster shortly after the Big Bang than we predict, which might require new forces and particles. Because we believe we understand how gas, that is atom-based matter, infalls onto these early galaxies, and how star formation feeds back and prevents future gas from falling in. There's a limit for how fast material can accrete onto these objects, and although certain physical conditions can lead to an object temporarily overcoming that limit, it shouldn't be sustainable over such long timescales. Indeed, we typically see a maximum of 10% of gas converted into stars. But for galaxies to form so fast at such a size, they also would need to be converting nearly 100% of their available gas into stars. So, while 100% conversion of gas into stars is technically right at the edge of what is theoretically possible, it's really the case that this would require something to be very different from what we expect. A lot of people immediately assert that all of standard cosmology might be wrong, and perhaps we should throw out the Big Bang as the explanation for the origin of our universe as well. They hypothesize new laws of physics, like a new early form of dark energy that existed early on, or new physical phenomena, like the universe being born with supermassive black holes, or new exotic forms of matter, like a novel, long-lived particle that decays into normal matter at relatively late cosmic times. While many people believe that the explanation is a perfectly absurd, that is not the case. Remember that even before the historical launch of James Webb, a number of problems arose with our current standard model of cosmology as follows. 1. Nature of dark matter. One of the fundamental issues with the LCDM model is the nature of dark matter itself. Dark matter has not been directly observed. Its existence is inferred from gravitational effects on visible matter and the cosmic microwave background. Despite extensive searches using various detection methods, including direct detection experiments and indirect astronomical observations, the particle or particles that constitute dark matter remain unidentified. 2. Dark energy and cosmological constant. The inclusion of a cosmological constant lambda to explain the accelerated expansion of the universe is another contentious point. Originally introduced by Einstein and later discarded, lambda was revived after observational evidence suggested an accelerating universe in the late 1990s. The challenge lies in reconciling the extremely small value of lambda predicted by quantum field theory with the observed energy density of dark energy, leading to what is known as the cosmological constant problem. 3. Structure, formation, and simulations. While the LCDM model successfully predicts the large-scale structure of the universe and the distribution of galaxies, discrepancies arise on smaller scales. Simulations of structure formation sometimes overpredict the number of small satellite galaxies around larger galaxies like the Milky Way. This missing satellite problem suggests that either our understanding of dark matter is incomplete, or the simulations need additional refinement, such as including baryonic physics, ordinary matter, more accurately. 4. Cusp versus core problem. Another issue within the LCDM framework is the cusp versus core problem in the density profiles of dark matter halos. Simulations tend to predict a cuspy central density profile for dark matter halos, whereas observations of dwarf galaxies and other structures hint at a more cored profile. This discrepancy raises questions about the effects of baryonic feedback processes, such as supernovae and black hole formation, on dark matter distribution, which are not fully understood or included in current simulations. 5. Tension in Hubble constant measurements. Recent measurements of the Hubble constant, which describes the rate of expansion of the universe, have shown a persistent tension between values obtained from local measurements, using objects like Cepheid variables, and those inferred from the cosmic microwave background by the Planck satellite. This tension suggests potential shortcomings in our cosmological models, including LCDM, or the presence of systematic errors in measurements that are yet to be resolved. Beyond these specific challenges, the LCDM model also leaves unanswered some fundamental questions in cosmology. For instance, it does not explain the nature of inflation, the epoch of rapid expansion thought to have occurred shortly after the Big Bang, although inflation can be accommodated within the framework of LCDM with additional scalar fields. In addition, the singularity is also a big deal. The standard model gets stuck at the point before the Big Bang, because according to it, there is nothing before it. In a similar way, we don't know one-time only things that happened in history. Mathematically, the Big Bang looks like it came from an undefined state, something that isn't explained by the laws of physics under Einstein's theory of general relativity. This is also called a singularity. And to Paul Steinhardt, the professor of physics and director of the Princeton Center for Theoretical Science, co-authored a paper on this topic, a cyclic model of the universe. That's the mathematical equivalent of a red flag. We all learned in school, when you get 1/0 for an answer, you're in trouble, because that's a nonsense answer. You made a mistake. In a related problem, there's also some difficulty in reconciling the inflation theory with string theory and quantum mechanics. If the model correctly described the universe, other accepted frameworks of physics would agree with it. Instead, Steinhardt says they're at odds. When one's thinking about cosmology, you're often reaching across fields of thinking, which are quite distant, either on the astro side or on the fundamental physics side, and seeing, do they fit together? In this case, the cyclic model can help do this. A cyclic model of the universe is designed to solve some of the seemingly unsolvable problems of the Big Bang and inflation models. According to Stefan Alexander, a professor of physics at Brown University and the co-inventor of an inflation model of the universe based on string theory, it allows us to go beyond the Big Bang, but without any kind of magical philosophical issues, because time has always existed in the past. Scientists have proposed a cyclic model that could work mathematically in a few ways. Its core principles are these. The Big Bang was not the beginning of time. There was a previous phase leading up to it, with multiple cycles of contraction and expansion that repeat indefinitely. And the key period defining the shape of our universe was right before the so-called Bang. There you would find a period of slow contraction called the Big Crunch. So, instead of a beginning of time arising out of nothing, the cyclic model allows for a long period of time in the lead-up. It claims to fix the same problems as the inflationary theory did, but builds even further. For one thing, the existence of time before the Big Crunch removes the singularity problem, that undefined number. It also utilizes string theory and quantum fluctuations. Like the LCDM, a cyclic model would also account for dark energy, an unobservable force that scientists believe is behind the accelerating expansion of the universe. But in the cycle model of Paul Steinhardt with Neil Turok, things get a little more like science fiction. Two identical planes, or branes, in string theory, an object that can have any number of dimensions, come together and expand apart. We can observe the 3 dimensions of our plane, but not the extra dimensions of the other. Dark energy is both the force leading the branes into a collision, with separation between them. Expansion of the branes themselves follows, and dark energy draws them together again once they're as flat and smooth as they can become. However, other scientists aren't so sure because of some of the assumptions this model brings in from string theory. Instead, some of them prefer another cyclic model from Roger Penrose, a theoretical physicist at Oxford, who came up with what Penrose himself called an outrageous new perspective on the universe. It's hard to wrap your head around. In the distant future, our solar system and galaxy will be engulfed by black holes, which eat up all the other mass in the universe, and then after an unimaginable amount of time, only black holes will exist. Eventually, only photons exist, which have no mass and therefore no energy or frequency, according to our accepted laws of physics. Penrose explains that measurements of scale no longer apply at this stage, but the shape of the universe remains. At the moment of the Big Bang, Penrose argues that when particles are so hot and close together that they also move at almost the speed of light, they also lose their mass. This creates the same conditions at the Big Bang as the cold, distant future universe. Their scale is no longer relevant, and one can beget the other. The remote future and the Big Bang become one and the same. Ultimately, what humans can observe of our universe is limited. That's why theories of the universe are never complete. We currently have a cosmology that is a glass that is 5% full. We have no idea whether the missing 95% due to a hypothesized dark matter, hypothesized dark energy, our lack of understanding of quantum mechanics, due to interactions from other dimensions, due our misunderstanding of time or other misunderstanding. Put simply, nature, the universe, is too complex to ever fully understand. But in the big picture of cosmology, there are possibly new insights that can lead to a fuller understanding of the universe and lead to a cosmology that is maybe even a glass is 25% full rather than just the 5% full of the current LCDM standard model of cosmology. We don't have to achieve an understanding of the universe that is a glass 95% full. Right now, the dozens of piece parts of cosmology are mostly correct and slowly, incrementally increasing their understanding. But the stitching together of those pieces constrains, actually cripples, scientific imagination. When that cosmological model is promoted as true, and necessary for the advancement of our understanding of the universe. It took a long time for science to overcome the crippling hypotheses of the flat Earth, the Ptolemaic epicycles, the biblical age of the universe as 4,000 years, the biblical story of creation of the plants and animals, and so on. And right now, the LCDM model is crippling astronomy and physics. We do not know how long it takes for a supermassive black hole to form, but black hole astrophysicists who dive into the details have avoided publishing their results because such an answer, for instance of maybe 200 billion years, is cosmological heresy in a universe that is supposed to be only 13.8 billion years old. So, we don't know is not an honest answer. It is an evasive answer by an astrophysicist community which wishes to avoid the wrath of the politically correct cosmological community. Why are there no published calculations or estimates of the time required to form a supermassive black hole? Remember what happened to S. Chandrasekhar, the student who took on the world's top astrophysicist, the Guardian Oct 19, 2017. Basically, Chandrasekhar's and others' study of black holes was destroyed because Sir Arthur Eddington destroyed Subramanian, Chandrasekhar's career, because Eddington, the great man, decided that nature would prevent black holes. Chandrasekhar got his PhD in astronomy, but could find no job in astronomy in England. So he left black hole research, left England, and won a Nobel Prize for his work on white dwarfs in 1983. The study of black holes did not become a respectable field of study. Sir Arthur died in 1944. Epilogue: after his white dwarf study, and after the golden age of black hole research was over, Chandrasekhar began to study black holes again. This time he was mocked by the young theorist who thought that nothing new was to be discovered about black holes. A second time, Chandrasekhar proved the dominant view wrong and opened up a renaissance in black hole research. Astrophysicists dare not ruin their careers, but estimating the time it takes for a supermassive black hole to form, based on our current knowledge. Twice, Chandrasekhar demonstrated Galileo's truth. In questions of science, the authority of 1,000 is not worth the humble reasoning of a single individual. On the other hand, as our technology rapidly advances, observations that support or detract from one model or another come more often. It's completely worth making all this speculation in this work, because we are getting to the point in which this data will arrive. One such observation could produce compelling support for either a cyclic model or confirm the more accepted inflationary theory. Because of how matter is distributed in our view of the oldest part of the universe, gravitational waves that reach us may be polarized, like light, at a particular frequency. Soon, within a few years, in fact, scientists may be able to determine whether this polarization exists. If it does, it will support the inflationary model. If this polarization doesn't exist, it will undermine slow contraction, a hallmark of the cyclic model. We'll be one step closer to making sense of time and space, yet still on a journey within the cosmos that's far from over. As a quick note, besides James Webb and next-gen telescopes, CERN also plays a key role in the quest to lift the veil on the universe's secrets. Planning is well underway for the successor to the world's most powerful particle accelerator, the Large Hadron Collider, known as LHC. The new atom smasher, named the Future Circular Collider, or FCC, will dwarf the LHC in size and power. It will smash particles together with so much energy. In fact, LHC operators at CERN revealed the results of a midterm review of their FCC feasibility study to the press. The feasibility study began in 2021 and is set to conclude in 2025. The findings thus far constitute 3 years of work, with scientists and engineers from across the globe determining the placement of the new accelerator's ring, the implementation of the FCC facility, concepts for detectors and funding aspects. The FCC will run under the jurisdiction of France and Switzerland, just like the LHC currently does, but the future accelerator will stretch 90.7 kilometers, making it over 3 times the length of CERN's current particle accelerator, which is 27 kilometers long. The LHC is the largest and most powerful particle accelerator in the world. The FCC will operate in the same way as the LHC, accelerating charged particles around a loop using superconducting magnets, then smashing them together as they approach the speed of light. Scientists can probe fundamental physics by observing showers of secondary particles created when particles like protons slam together. But whereas the LHC can attain energies of around 13 tera-electron volts when operating at full power, CERN says the FCC should be able to reach energies as great as 100 tera-electron volts. Its aim is to study the properties of matter at the smallest scale and highest energy. The crowning achievement of the LHC thus far is undoubtedly the discovery of the Higgs boson, the force-carrying particle of a field called the Higgs field, which permeates the universe and dictates most other particles' masses. The breakthrough sighting of the Higgs boson by 2 LHC detectors was announced on July 4, 2012, and is credited with completing the standard model of particle physics, which is humanity's best description of the universe, its particles and their interactions on a subatomic scale. Yet, the standard model still requires some tweaking, and since 2012, scientists have been using the LHC to search for physics beyond the model to make those adjustments. Success has been limited. This search will get a boost when the LHC's high luminosity upgrade is completed, which will mean the particle accelerator can perform more collisions and offer scientists more opportunities to spot exotic physics. The 2 main outliers of the standard model are dark matter and dark energy. Sometimes collectively known as the dark universe, these phenomena constitute such large mysteries for scientists because dark energy accounts for around 68% of the universe's energy and matter, while dark matter accounts for around 27% of these continents. But neither can be seen because they don't interact with light, and no one has been able to pin them down through other forms of direct detection either. That means that the matter and energy we understand and can account for comprise no more than 5% of the universe's contents, and we have little idea what around 95% of the universe actually is. And probing these aspects of the universe may require smashing particles together with much more energy than the high luminosity LHC is capable of. To begin with, dark matter can't be standard matter, like the atoms that make up the stuff we see around us on an everyday basis, like stars, planets, and our bodies. Remember how it doesn't interact with light? Well, protons, neutrons, and electrons, collectively known as baryons, do. So dark matter must be something else. Currently, the only way scientists can infer the presence of dark matter is via its interaction with gravity and the effect this has on baryonic matter, and in turn, light. Dark energy is even more problematic. It's the force that scientists see driving the acceleration of the universe's expansion. It concerns a period of expansion separate from the universe's initial inflation, which was triggered by the Big Bang. After that early expansion slowed to a near halt, in a later epoch, the universe unexplainably started to expand again. This expansion rate is actually speeding up to this day, with dark energy used to account for that action. But as we've discussed, scientists don't actually know what dark energy is. To see why that is troubling, imagine pushing a child on a swing. The Big Bang is akin to your first and only push that gets the swing in motion. The swing may keep going for a short while, even without any action from you. Then it will come to a half. Then imagine that it suddenly begins motion again, despite you just standing there. And not only that, but it swings faster and faster, reaching higher and higher points. This is similar to what dark energy is doing to the very fabric of space. CERN hopes the high-energy collisions of the FCC could reveal the nature of this ongoing late-universe push and the particles that make up dark matter. However, it will be some time before this future particle accelerator is ready to embark on its investigation of the dark universe.
One of the biggest and most heated cosmic debates of our time surrounds a peculiar dilemma with a rather snappy name: Hubble tension. This phrase describes the fact that even though scientists are aware the cosmos is constantly ballooning outward in every direction, as we can clearly see stars and galaxies drifting farther and farther away from us over time, they can't perfectly pin down the rate at which that ballooning is happening. That leaves us with a pretty major chasm in our understanding of the universe. Evidence of this conundrum has been accumulating for years, causing some researchers to call it a looming crisis in cosmology. And when James Webb launched into space, scientists expected the telescope could help clarify one of the biggest puzzles in modern astronomy. In an attempt to get to the bottom of this, researchers recently just announced that the James Webb Space Telescope has weighed in on the situation for the first time, but it did not solve the mystery. In fact, JWST actually thickened it. Join us today as we dig deep into how the James Webb Space Telescope just made the crisis in cosmology worse. For most of human history, the study of cosmic origins was a matter of myth, variations on the theme of "in the beginning." In 1925, American astronomer Edwin Hubble edged it toward empiricism when he announced that he had solved a centuries-long mystery about the identity of smudges in the heavens, what astronomers called nebulae. Were nebulae gaseous formations that resided in the canopy of stars? If so, then maybe the canopy of stars, stretching as far as the most powerful telescopes could see, was the universe in its entirety. Or were nebulae island universes all their own? At least one nebulae is, Hubble discovered, what we call today the Andromeda Galaxy. Furthermore, when Hubble looked at the light from the other nebulae, he found that the wavelengths had stretched toward the red end of the visible spectrum, suggesting that each source was moving away from Earth. Noting that the speed of light remains constant, what changes is the length between waves, and that length determines color. In 1927, Belgian physicist and priest Georges Lemaitre noticed a pattern. The more distant the galaxy, the greater its redshift. The farther away it was, the faster it receded. In 1929, Hubble independently researched the same conclusion. The universe is expanding. But expanding from what? Reverse the outward expansion of the universe, and you eventually wind up at a starting point, a birth event of sorts. Almost immediately, a few theorists suggested a kind of explosion of space and time, a phenomenon that later acquired the initial derogatory moniker Big Bang. The idea sounded fantastical, and for several decades, in the absence of empirical evidence, most astronomers could afford to ignore it. That changed in 1965, when two papers were published simultaneously in the Astrophysical Journal. The first, by 4 Princeton University physicists, predicted the current temperature of a universe that had emerged out of a primordial fireball. The second, by 2 Bell Lab astronomers, reported the measurement of that temperature. The Bell Lab's radio antenna recorded a layer of radiation from every direction in the sky, something that came to be known as the cosmic microwave background, or CMB. The temperature the scientists derived from it, of 3 degrees above absolute zero, did not exactly match the Princeton collaboration's prediction, but for a first try, it was close enough to quickly bring about a consensus on the Big Bang interpretation. In 1970, one-time Hubble protege Alan R. Sandage published a highly influential essay in Physics Today that in effect established the new science's research program for decades to come. Cosmology, a search for 2 numbers, it was called. One number, Sandage said, was the current rate of the expansion of the universe, the Hubble constant. The second number was the rate at which that expansion was slowing down, the deceleration parameter. Scientists settled on a value for the second number first. Beginning in the late 1980s, two teams of scientists set out to measure the deceleration by working with a common assumption and a common tool. The assumption was that in an expanding universe full of matter interacting gravitationally with all other matter, everything tugging on everything else, the expansion must be slowing. The tool was type Ia supernova, exploding stars that astronomers believed could serve as standard candles, sources of light that do not vary from one example to another, and whose brightness tells you its relative distance. A 60-watt light bulb, for example, will appear dimmer and dimmer as you move further and further away from it. But if you know it is a 60-watt bulb, you can deduce its separation from you. If expansion is slowing, the astronomers assumed, at some great length away from Earth, a supernova would be closer, and therefore brighter, than if the universe were growing at a constant rate. What both teams independently discovered, however, was that the most distant supernova were dimmer than expected and therefore farther away. In 1998, they announced their conclusion. The expansion of the universe is not slowing down, it is speeding up. The cause of this acceleration came to be known as dark energy, a name to be used as a placeholder until someone figures out what it actually is. A value for Sandage's first number, the Hubble constant, soon followed. And for several decades, the number had been a source of contention among astronomers. The expansion rate of the universe can be a confusing concept that is, perhaps, best introduced by analogy. Suppose you have a rubber band that is 2 units long, with a mark at the center. You attach one end of the band to an unmovable hook and hold up the other end to ensure that it is straight. Thus, the end you are holding is 2 units away from the hook, while the mark is 1 unit away. Then imagine that you grab the loose end and stretch it so that it is double the length, taking 1 second to do it. The end is now 4 units away from the hook, while the mark at the center is 2 units away. Thus, the mark moved 1 unit in 1 second, while the loose end moved 2 units in a second. The key point is that the spot more distant from the hook moved more quickly than the one near the hook. In the language of cosmology, the velocity of a spot on the rubber band is 1 unit per second for every unit of distance from the hook. The expansion of the cosmos is exactly the same. More distant objects in the universe are moving away from Earth quicker than closer ones. In round numbers, distant galaxies move away from Earth at a rate of 70 kilometers per second for every million parsecs of distance. A parsec, as a reminder, is a historical unit of astronomical distance equal to 3.26 light years. Thus, a galaxy at 1 megaparsec from Earth moves away at a rate of 70 kilometers per second. A galaxy 2 megaparsecs away moves at a rate of 140 kilometers per second. This rate is called the Hubble constant, and the basic idea is very well established. However, there are several ways to determine the Hubble constant. The first and most straightforward way is to measure the distances to galaxies and simultaneously measure their velocity. You can then determine the galaxies' velocities as a function of distance. When you do this, you find that the Hubble constant has a value of about 73 plus or minus 1 kilometers per second per megaparsec. Different groups obtain slightly different values, but they are all quite consistent. This value of the Hubble constant is called the late time version, as it is determined from the period relatively late in the lifetime of the universe. There is another way to determine the Hubble constant by examining the conditions of the cosmos shortly after it began. The universe began 13.8 billion years ago in a cosmic cataclysm called the Big Bang. While it is somewhat misleading, one can imagine the Big Bang as a vast explosion, which included a glowing fireball and a rumbling sound. In the very early universe, the fireball was impenetrable, but when the cosmos was a mere 0.003% its current age, the expansion cooled the universe enough that light could escape the fireball and travel across the cosmos. While the universe was glowing hot at that early time, the expansion of space over the eons has cooled it until the light is no longer visible. Indeed, that once visible light is now only microwaves, which can be detected by radio antennas. This primordial whispering remnant of the Big Bang is called the cosmic microwave background, or CMB, and it was first detected back in 1964. The sound waves of the Big Bang were locked into the early fireball, resulting in tiny variations in the CMB. Astronomers can measure those variations very precisely. Using those patterns, they can take all factors known to have any relevance to the Big Bang and subsequent evolution of the universe and predict a value of the Hubble constant for our current day. This approach hinges crucially on the measurements of these variations in the CMB, as well as various theoretical ideas. Using this early time information, astrophysicists predict that the Hubble constant should be about 67.5 plus or minus 0.5 kilometers per second per megaparsec. And there's the rub, they say. The early time and late time measurements simply disagree, and this specifically is what is referred to as the Hubble tension. Disagreements tend to generate excitement in the astronomical community because a discrepancy of this magnitude could mean theories need to be rethought altogether. In other words, there is more science out there to discover. Potentially, this discrepancy either suggests our instruments are not intelligent enough, or maybe we're awfully wrong about that theoretical prediction. In other words, perhaps the models that presently thread our understanding of the universe are missing something. In 2019, a number of high-profile physicists even famously gathered at the Kavli Institute for Theoretical Physics in California to officially try and resolve things. That ended with a headache. As particle physicist David Gross, a former director of the KITP, put it, "We wouldn't call it a tension or a problem, but rather a crisis." And ever since, scientists have continued to diligently work out where they might have gone wrong, crossing off possible explanations for Hubble tension on a list you can check out here. But when James Webb opened its eyes on the cosmos, it crossed one more item off that list. In a nutshell, it showed that the so-called crisis is probably not due to technical issues with measurements made by its telescope sibling that boasts a very relevant name, the Hubble Space Telescope. As Adam Rees from the Johns Hopkins University and the Space Telescope Science Institute said in a statement, "Webb measurements provide the strongest evidence yet that systematic errors in Hubble's Cepheid photometry did not play a significant role in the present Hubble tension." This is a big deal because Hubble observations are one of the most common features that scientists use to decode the Hubble constant, or more specifically, Hubble observations of Cepheid stars are. Hubble is a key device used in resolving Hubble tension because it's able to measure stellar brightness with incredible precision. That's because it sits above Earth's blurring atmosphere, unlike ground-based observatories hampered by our planet's hazy shield. Such brightnesses can tell us how far away those stars are and, because we know the immutable speed of light, for how long that light has been traveling to reach us. After some calculations, scientists reasoned that this kind of information taken from lots and lots of stars should help us figure out the Hubble constant. Rees explains, prior to Hubble's 1990 launch, the expansion rate of the universe was so uncertain, astronomers weren't sure if the universe has been expanding for 10 or 20 billion years. Furthermore, there's one star in particular that scientists like to focus on with Hubble to tease out the universe's expansion rate: Cepheids. These are supergiant stars with something like 100,000 times the luminosity of our Sun. They are the gold standard tool for the purpose of measuring the distances of galaxies 100 million or more light years away, Rees said, calling such measurements a crucial step to determine the Hubble constant. Rees also mentioned that Cepheids pulsate, expand and contract in size, which indicates their relative luminosities. The longer the period, he explained, the intrinsically brighter they are. And this is good because it provides baseline brightnesses and ultimately more accurate measurements. So, thanks to Hubble's perch above our atmosphere, the telescope can identify individual Cepheids in galaxies more than 100 million light-years away, thus measuring the time interval over which these galaxies change their brightness. But Hubble has its limitations. It's not quite sensitive enough to infrared light wavelengths, which are found beyond the red end of the electromagnetic spectrum and remain invisible to human eyes. According to Rees, unfortunately, Hubble's red light vision is not as sharp as its blue, so the Cepheid starlight we see there is blended with other stars in its field of view. Infrared vision is important when peering at faraway objects because, first of all, light coming from distant sources gets stretched out on the way to our vantage point on Earth. Once tight bluish wavelengths turn into longer, reddish ones. That's exactly where the term redshift galaxies come from, referring to realms falling deeper toward that end of the spectrum from our ground-based perspective. And second, only infrared light has the ability to pass through dust unscathed, meaning if a Cepheid is stuck behind a shroud of interstellar matter, it would appear fainter to us. That runs the risk of its light blending in with light from another Cepheid in the vicinity, for instance, or making it seem like a star is farther away than it truly is. We can account for the average amount of blending, statistically, the same way a doctor figures out your weight by subtracting the average weight of clothes from the scale reading, Rees says, but doing so adds noise to the measurements. Some people's clothes are heavier than others, for example. Enter the James Webb Space Telescope, the JWST. This $10 billion observatory sitting nearly 1 million miles, that's 1.6 million kilometers away from Earth, is built to unveil the infrared universe to us. In the first year of Webb operations with our General Observers Program 1685, we collected observations of Cepheids found by Hubble at 2 steps along what's known as the cosmic distance ladder, Rees said. The first step, according to the team, involved observing Cepheids in a galaxy with a known geometric distance for calibration purposes. That galaxy was NGC 4258. The second step was to observe Cepheids in the host galaxies of recent type Ia supernovas, which are bright star explosions, to basically double-check whether Hubble's observations were right. If Hubble was wrong, well, maybe we finally learned why there's a discrepancy. But Hubble's observations were right. JWST, I think, has really kind of put a nail in the coffin of, was there a problem with Hubble's Cepheid measurements, Rees said, while presenting the research at the JWST's First Year of Science conference. Regardless of the final explanation, the Hubble tension is shaping up to be a fine mystery. And if the Hubble tension really does reflect our physical reality, then explaining it will probably require adding another item to our list of the universe's fundamental ingredients. And of the leading theoretical contenders, called early dark energy, proposes that about 50,000 years after the Big Bang, there was a brief flare-up of dark energy. In principle, a short blip of extra dark energy could alter the expansion of the early universe enough to resolve the Hubble tension without messing too much with the standard model of cosmology. But in the process, cosmologists' estimate for the age of the universe would fall from the current 13.8 billion years to about 13 billion years. According to Mike Boylan-Colchin, an astrophysicist at the University of Texas at Austin, there's a lot of questions about why you have to introduce this one new thing that just shows up and disappears. That feels a little funny. But we're in a place where, if these things are really that discrepant, maybe we have to start looking in the funny corners of the universe, he said. For now, there's no slam-dunk evidence for early dark energy, so future observations will be required to get to the bottom of the mystery. Other observatories should also help clarify the Hubble tension. Ongoing efforts continue to try to refine both the early and late-time estimates of the Hubble constant, and it will be some time before the question is resolved. Although the expansion rate is still unknown, one thing is certain: the universe is expanding. But if it is expanding, what is it expanding into? The short one-word answer to this question is as pithy as it is unsatisfying: itself. The universe is everything, so it isn't expanding into anything. It's just expanding. All of the galaxies in the universe are moving away from each other, and every region of space is being stretched. But there's no center they're expanding from, and no outer edge to expand into anything else. But that doesn't mean that the universe is infinite. That brings us to the long answer. To understand how something could be finite but have no edge, think of the fabric of the universe as the surface of a balloon. As the balloon inflates, the surface stretches and every point on that surface moves away from every other point. But a tiny being on the surface of that balloon could walk forever and never run into the edge of its balloon universe. There's no edge, yet that balloon universe has a finite volume. But the balloon is just one example. Scientists aren't actually sure whether the universe is finite or infinite, or even what shape the universe is. There are three options: spherical, flat, or hyperbolic. That is, it curves upward. Evidence from the earliest light in the universe suggests that the second option is on the money, and the universe is, in fact, flat. Even if the universe is flat and not balloon-shaped, however, it's still easy to think about how it could be finite with no edge. Think about a flat piece of paper. You could take two opposing edges and make them touch, creating a cylinder. If a tiny two-dimensional rocket ship traveled from one of those edges to the other, it would arrive back where it started. You could do the same thing in perpendicular direction. Connect the two ends of the tube to each other and create a donut shape, also known as a torus. Now your two-dimensional rocket ship could travel anywhere it likes, and it would never encounter an edge, even though your paper torus has finite volume. But wait, you might be saying, paper's flat, a torus is curved. Isn't that cheating? Well, no, and that's because scientists have a very specific definition for the word flat. When they say flat, they mean Euclidean, which means that parallel lines always run parallel, and the sum of the angles of a triangle is always exactly 180 degrees. This doesn't happen on a sphere or a hyperbola, but it does on a cylinder, a torus, and any other shape you can make out of a flat piece of paper. This suggests something kind of exciting, doesn't it? If we live in a flat universe, you could potentially travel in one direction for long enough, or build a telescope that can see far enough, to end up right back where you started. Even cooler things happen when you think about other weird shapes. Shapes that twist back on themselves could make you arrive at a mirror image of where you started, for example. But no matter what the shape of the universe is, it's not expanding into anything. There's nothing outside of the universe because the universe, again, has no edge.
In 1930, the concept of dark matter and dark energy was first introduced by Fritz Zwicky. The influence of these two sources of matter and energy on the formation of stars and galaxies has been supported by numerous observations and discoveries in modern cosmology. However, every cosmological model has its own shortcomings. The unique existence of an ancient galaxy completely devoid of dark matter is a significant blow to the astronomical community. It is challenging the efforts of scientists to answer the question, where does the origin and existence of the universe come from after billions of years? The presence of a dark matter-free galaxy raises many hypotheses about humanity's understanding of the vast 95% of the universe. Does this affect the process of sustaining the existence of the galaxy itself? And what does the future hold in store for us? Does dark matter truly exist, or is it just an excuse, a condition for the current limitations of humanity's knowledge? Let's explore the latest discoveries in this field to gain a deeper understanding of the vast universe and the significance of dark matter in maintaining the existence of magnificent galaxies. This is EYES 200M, and welcome back to join us on this journey. NGC 1277, the relic of the primordial universe. Dark matter and ancient galaxies. It's the enigma that has puzzled many scientists and astronomers of the 21st century. Discovering and observing these distant remnants is incredibly challenging due to the limitations of scientific technology. However, thanks to the presence of the James Webb Space Telescope, or JWST, humanity has been able to venture further in the search and exploration of the oldest relics in the universe, galaxies formed shortly after the Big Bang. Before the JWST embarked on its noble mission, NGC 1277 was just one of the faint red smudges in the southern sky as seen through the lens of the Hubble telescope. It was one of over 700 ancient galaxies captured by James Webb in early June. NGC 1277 is a dwarf elliptical galaxy located in the constellation of Andromeda. It is a member of the Perseus cluster and lies approximately 220 million light-years away from us. NGC 1277's apparent magnitude is around 14.7. It was discovered on December 4th, 1875, by Lawrence Parsons, the 4th Earl of Rosay. NGC 1277 is unique in that it is considered a relic of what galaxies were like in the early universe. The galaxy is composed exclusively of aging stars that were born 10 billion years or so ago. But, unlike other galaxies in the local universe, it has not undergone any further star formation. Astronomers nickname such galaxies as red and dead because the stars are aging and there aren't any successive generations of younger stars. The telltale sign of the galaxy's arrested development lies in the ancient globular clusters that swarm around it. The reddish clusters are the strongest evidence that the galaxy went out of the star-making business long ago. Otherwise, there would be a lot of blue globular star clusters, which are largely absent. The lack of blue clusters suggests that NGC 1277 never grew further by gobbling up surrounding galaxies. To be fair, our understanding of the grand relics of the universe, like NGC 1277, is far too limited. Before shocking the world with its meager dark matter content, NGC 1277 had perplexed many scientists with data concerning the supermassive black hole residing at its core. Recent findings indicate that the black hole at the center of the galaxy NG 1277 seems to account for about 59% of the total galaxy mass, the largest fraction of any supermassive black hole ever measured. It harbors a black hole with an approximate mass of 12 billion times that of our Sun. This far exceeds the expected mass of the central black hole in a galaxy of the modest dimensions of NGC 1277. We suggest that this giant black hole was ejected from the nearby giant galaxy NGC 1275 and subsequently captured by NGC 1277. The ejection was the result of gravitational radiation recoil when two large black holes merged following the merger of two giant ellipticals that helped to form NGC 1275. The black hole wandered into the cluster core until it was captured in a close encounter with NGC 1277. The migration of black holes in clusters may be a common occurrence. Most massive galaxies have supermassive black holes at their centers, and the masses of the black holes are believed to correlate with the properties of the host galaxy bulge component. Several explanations have been proposed for the existence of these locally established empirical relationships, including the non-causal statistical process of the galaxy merging, direct feedback between the black hole and its host galaxy, and the subsequent violent relaxation and dissipation. The empirical scaling relations are therefore important for distinguishing between various theoretical models of galaxy evolution, and they furthermore form the basis for all black hole mass measurements at large distances. Observations have shown that the mass of the black hole is typically 0.1% of the mass of the stellar bulge of the galaxy. Until now, the galaxy with the largest known fraction of its mass in its central black hole, 11%, was the small galaxy NGC 4486 b1-9. From observational experience, the existence of the central black hole in NGC 1277 remains a significant mystery. It is still unclear whether these galaxies represent the tail end of distribution, or if galaxies with dominant central black holes deviate from the typical mass black hole relationship seen elsewhere. When James Webb focused its observation on NGC 1277, scientists immediately recognized a significant issue from the images. The existence of a massive black hole led to parameters indicating that NGC 1277 is entirely devoid of dark matter. Is this a normal relationship in the universe, or are there still hidden secrets? Can black holes truly consume even the components known as dark matter? Or, fundamentally, does dark matter and dark energy not exist? If you are truly curious about what dark matter and dark energy have done to sustain the existence and formation of galaxies, I encourage you to check out the video James Webb Unveils the Mysterious Link Between Dark Energy and Black Holes in the Formation of Ancient Galaxy Clusters on our channel. The link will be provided right below the description for you. But for now, let's delve into the evidence from NGC 1277 to discover what is truly happening inside this ancient galaxy. I hope you'll keep an open mind, as what we are about to reveal may challenge some of your beliefs, what you've heard, and what you've learned so far. NGC 1277 has a severe dark matter deficiency. In the current standard model of the universe, dark matter and dark energy account for approximately 95% of the total mass in the universe, meaning only about 1/6 is composed of the ordinary matter that we interact with in our daily lives. Dark matter remains elusive. It does not interact like regular matter, and its existence is solely inferred from its gravitational effects on stars and gas in galaxies. According to the Lambda CDM cosmological model, present-day galaxies with stellar masses greater than 100 billion times that of the Sun likely contain a substantial amount of dark matter within their stellar bodies. Models indicate that in massive early-type galaxies, or ETGs, with masses around 115 billion times that of the Sun, dark matter must account for approximately 15% of the dynamic mass within one effectual radius, or 1 RE, and about 60% within 5 REs. Most giant ETGs, or early-type galaxies, have been shaped through a two-phase process: a rapid formation of a compact core, followed by the accumulation of an extended outer envelope through mergers. Extremely rare galaxies have managed to avoid the second phase, known as relic galaxies, believed to be the frozen remnants of giant ETG populations at Z is greater or less than 2. The best known candidate for a relic galaxy discovered so far is NGC 1277, located in the Perseus cluster. NGC 1277 is a relic galaxy, a galaxy that does not interact with neighboring galaxies. Relic galaxies are exceedingly rare and are considered vestiges of giant galaxies formed in the early universe. Scientists have utilized data from the George and Cynthia Mitchell spectrograph, or GCMS, Deep Field Integral Field Spectroscopy, to re-examine NGC 1277 at an unprecedented radius of 6 kpc, equivalent to 5 effective radiuses, or 5 REs. By employing a model called anisotropy genes modeling, they found that dark matter contributes insignificantly within the range of 5 REs, which contradicts the predictions of the Lambda CDM cosmological model, Cameron explained. The significance of relic galaxies in helping us understand the formation of the early universe is the reason why we decided to observe NGC 1277 using integral field spectroscopy. From the spectra, we constructed dynamic maps that enabled us to understand the distribution of mass within the galaxy up to a distance of approximately 20,000 light-years. According to their findings, NGC 1277 contains no more than 5% of dark matter. Its mass distribution is solely determined by its stars. Current cosmological models predict that a galaxy of this size should have been between 10 to 70% dark matter. Dr. Ignacio Trujillo, a researcher at IAC and ULL, stated, "The discrepancy between the observations and what we expected is a puzzle, and it may even pose a challenge to the standard model." The research team proposed two possibilities to explain the lack of dark matter in NGC 1277. Dr. Anna Ferre-Matau, also from IAC and ULL, added, "One possibility is that gravitational interactions with the surrounding environment in the galaxy cluster containing this galaxy have stripped away the dark matter. The absence of an extended outer envelope reduces dynamical friction and prevents the accumulation of the outer layer. Therefore, Dr. Ferre-Matau suggests that NGC 1277 may have lost its dark matter very early on, or that it never had much dark matter to begin with. Scientists are currently discussing their discovery within the context of recent proposals, suggesting that some relic galaxies may result from dark matter being stripped away as they fall into and interact with galaxy clusters. Moreover, NGC 1277 could have been formed through a high-speed collision of gas-rich progenitor galaxy fragments, where dark matter left behind a dispersed baryonic disk. Standard calculations suggest that a relative velocity of about 2,000 kilometers per second or so is needed for the second process to occur, and this could plausibly take place in the ancestors of today's rich galaxy clusters. The issue remains that dark matter could have been expelled from the system during the galaxy's formation through the merging of progenitor galaxy fragments, resulting in a relic galaxy. However, both theories have left researchers unsatisfied. Cameron stated, "The puzzle of how a massive galaxy could form without dark matter remains an enigma." They plan to continue observations using the William Herschel telescope at the Roque de los Muchachos Observatory on the Canary island of La Palma. Perhaps surprisingly, the clear absence of dark matter in NGC 1277 is further evidence for its existence and raises significant doubts about alternative theories proposed to explain the observed effects in galaxies, such as theories suggesting a slight modification of the law of gravity on large scales. While dark matter may be missing in specific galaxies, a modified law of gravity must be universal. It cannot have exceptions. Therefore, a galaxy without dark matter would reject this alternative dark matter hypothesis. This presents a challenge to the Lambda CDM model itself. How many more secrets are hidden in the universe? Are we behaving like those who condemned Galilee? The truth is that the universe is too wide and contains too many questions. That's why I asked you to keep an open mind, because we will see many other great changes. The relationships between dark matter, dark energy, and ancient galaxies. Dark matter and dark energy are believed to have influenced the formation and evolution of galaxies during the early epochs following the Big Bang. Although they remain subjects of ongoing research and are not yet fully understood, hypotheses about dark matter and dark energy have been proposed to explain certain physical phenomena that cannot be accounted for by ordinary matter and energy. According to current physical models, Dark matter is assumed to exert gravitational effects and play a crucial role in the formation of large structures in the universe, including galaxy clusters and cosmic filaments. Dark matter enhances the gravitational force in the universe, leading to the contraction and concentration of matter to form galaxies. Dark energy, on the other hand, is believed to have a repulsive effect on distant galaxies, contributing to the cosmic expansion between galaxies. Dark energy is a concept devised to explain the accelerating rate of expansion of the universe and why galaxies rotate around their axes at a certain speed without breaking apart due to centrifugal forces. According to this hypothesis, dark energy can provide an additional push, contributing to the formation of galaxy clusters and cosmic filaments. Dark energy enhances the gravitational force between objects in the universe, leading to the formation of large structures and uneven distribution of matter in space, resulting in the network of galaxies that we observe today. But how do we find them? Those entities that do not interact with regular particles and assert their role? Well, the answer lies in the past, with a fascinating journey that starts from the Coma Cluster. The Coma Cluster, also known as the Coma-Abel 1656 cluster, is one of the nearest and largest galaxy clusters that we know of. It lies in the constellation Coma Berenices and is approximately 320 million light-years away from Earth. It is also one of the richest galaxy clusters in the nearby universe. The Coma Cluster has an incredibly high galaxy density and contains many massive galaxies. On average, each volume of space within the cluster hosts about 10 to 15 galaxies. This means that in each smaller volume of the cluster, there exists a large number of galaxies clustered closely together. Well, what does this mean? According to the gravitational theory in physics, large galaxies within the Coma Cluster could move and merge within smaller galaxies at high speeds. However, galaxies within the cluster maintain stable velocities, and close galaxies can still avoid collisions and mergers. This contradicted previous calculations by space physicists. Hence, the concept of dark energy and dark matter emerged. According to the theory, dark matter interacts with regular matter through gravitational force. The presence of the matter in the Coma Cluster has caused galaxies to move slower than what was predicted by the gravitational force of regular matter alone. In the research paper, Strong and Weak Lensing United, the mass distribution of the merging galaxy cluster, 1 IES 0657-558, derived from joint X-ray and lensing analysis. Scientists use strong and weak lensing measurements to determine the mass distribution within the Coma Cluster. The research findings revealed the existence of dark matter in the cluster and its significant impact. As a result, we were able to ascertain the presence of a substantial amount of dark matter, estimated to make up around 90% of the mass of Coma. So, dark matter acts as a counterbalance, like a scale on the other side, to be in equilibrium with gravitational force. Put simply, if we were to remove dark matter, we would witness billions of galaxies colliding with each other every day. They would stop rotating around their axes and rush away from each other every second. Earth would also rush straight towards the Sun and become a part of it. This equilibrium has been maintained for billions of years since the birth of the universe. Evidence of this balance still exists in the images captured by the James Webb Space Telescope. There is only one reason to explain the current situation, and that is that we made a mistake right from the step of determining the types of particles and energy that make up the galaxies. We have been wrong from the very beginning of our theories. Scenarios of ancient galaxy formation. According to previous cosmological models, galaxies would continuously evolve and form new stars. However, Without dark matter, the sources of energy to form new stars would be limited. As a result, galaxies would lack younger star generations, and the existing stars would continue to age without any replenishment. Early proposed scenarios for the formation of large primordial galaxies indicated a monolithic collapse similar to what was suggested for the oldest stellar populations in the Milky Way. However, these models have become outdated with the emergence of cold, dark matter formation models in cosmology. Recent computational studies based on the Lambda CDM cosmological framework, however, suggest that nature borrows from both scenarios, and the process of forming massive ETGs, again, early-type galaxies, can be divided into two stages. Initially, the giant ancestors of ETGs undergo a dissipation-less collapse, resulting in a compact rotating object where star formation is quickly suppressed, possibly due to the activity of an active galactic nucleus, or AGN. In the second stage, the massive evolution of the stellar population transforms the blue-hued objects into red, and most of the stellar mass growth of the object comes from the accumulation of an extended outer shell supported by pressure through dry accretion. The account of this simplified two-phase formation is supported by observations indicating that galaxies evolve passively at higher redshifts, being much more compact than local massive ETGs, and they have grown 4 times in effective radius since redshift, or z is infinity more than 2. This framework is supported by the fact that stellar shells have been demonstrated to develop over cosmic time. Additionally, recent identifications of small, compact, star-forming and likely rotating super-red nuggets might provide further evidence for the two-phase formation scenario. Detailed studies of NGC 1277 have provided a unique and profound insight into the harsh conditions where nuggets develop. Martine Navarro and colleagues discovered that the initial mass function, or IMF, of NGC 1277 is the heaviest across all galaxies, implying a high mass-to-light ratio of stars. Similarly, slightly less extreme properties have been confirmed for 2 other relic galaxies. Furthermore, dynamical modeling revealed that almost no dark matter is needed to explain the dynamics of stars within the innermost 13 inches of NGC 1277. Conclusion. Thus, the relationship and correlation between dark matter and galaxies remains a mysterious puzzle that requires further exploration. The discoveries about NGC 1277 have provided valuable insights into the formation and evolution of relic galaxies. The evidence and models have revealed surprising and intriguing aspects concerning the dynamics, central black holes, and the development of dark matter in the universe. If you are still curious and eager to explore more about the latest discoveries in this field, stay tuned for our James Webb video about the enigmatic connection between dark energy and black holes in the formation of ancient galaxy clusters. In the meantime, we sincerely thank you for joining us today on this journey. Keep following and discovering the fascinating and novel aspects of the universe in the future. See you in upcoming videos. Thank you and have a wonderful day.